Hi, I'm Bill Hurd,
I'm Fran Blanche.
and we're not dead yet.
Not yet.
No. So we have some viewer mail we wanted to go over today, right?
Yeah,
Couple
viewer
items.
mail. People sent in some stuff for us to talk about.
Pretty cool stuff.
Pretty cool stuff, yeah. I was actually pretty amazed that this thing came in, but this is we have the.
Yeah, this is from Tom Smith, who
Yes.
was emailing you,
Yeah.
and he's got an immaculate Heath kit that he sent us. It's a tri-power supply, and we'll show you the inside here in a second because it's really a combination of the things from the day. Nowadays the switches you would hook straight to a PC board or something instead of wiring wires to it and everything. So it's all in there. It's a pretty cool unit, and it's very clean.
Well, not only is it clean, but he actually sent the receipt from
Right.
when he bought it from September 1991, which is kind of late for Heath kit. I'm not really sure when they stopped making kits, but it had to be like one of the last, because they changed over from doing kits to doing educational stuff
Right.
sometime in the 90s. But yeah, 91.
My favorite part, the schematic.
Oh yeah. With Heath kit, you would get everything. You get the schematic and a manual. It wasn't just a kit. But what is this model? What is it? It's a tri-supply set.
It has a 271B tri-supply. Now, it is linear. I'm going to show you the inside of it here in a second. But, back in the day, I was always trying to find a good 12-volt supply because I worked on car radios or, CBs and car stereos. But then after that, it was a 5-volt supply you needed, and then tracking analog. So if you didn't get this from Heath kit, there weren't a lot of places you'd get one of these. Something like this. You'd have to do what I do, which is collect all kinds of different modules.
Yeah, well, I built a lot of power supplies over the years, and I ended up building my own dual supply.
Right.
But this one is pretty much for the day. This is what's 5-volt, has 5-volt fixed, right? And then is it variable? Yeah,
It's variable. It's got a clutch so that you can track, and then it's got an amperage control.
Okay.
Which the ones I built when I was young didn't allow you to control amperage like we do, which keeps you from burning stuff up 1 out of 20
so
times.
So it has active current control in addition to the voltage control.
Right, which is probably what most of the transistors here are for.
Yeah, I noticed that it's got the bank on the back.
Yeah, you can.
I guess we should zoom in on the supply.
Yeah, we can. So here's the inside.
We should show the. Okay, we got it on there.
Yeah, and you can see the combination where we've got the strips like we used to use. TV sets were built with these, right?
I'm still using those.
There you go. And big old caps, and it's all about the transformer in the old days.
Exactly.
Nowadays it's hard to find transformers. And then there's a circuit board you can see right there, and that's the voltage and the amperage control circuitry for the most part on here.
That's typical Heath single-sided fashion with the silkscreen on one side, all the copper on the other.
Yep, let me get it recentered. Here, let's do
There's
that.
the panel. Look at that panel. Really a thing of beauty.
Yep.
Yeah. And on the back too, it's got the heat-sinked transistors. Obviously, you got 2 for voltage and 1 for current, right?
It's 1 for each output. So one is a 5-volt regulator, and then one is for the. They look like standard common base supplies, with the current control. The thing about these. The thing about these is being linear. This actually would have run hotter if you're trying to make 6 volts at 1 amp than if you're making 12 volts at 1 amp. Because it's all about the transformer starts from a voltage, and then those heat sinks or the transistors in the back have to get rid of all the extra.
Right. That's one of the things that people these days, we're just starting out in electronics,
Take
learn.
for granted.
Yeah. Well, everyone wants to make a 5-volt supply now, or 3.5-volt supply. These low voltages, but most of the transformers are going to come up with 12 volts or 6 volts. So the huge heat sink is something I guess that people learn first off about linear supplies.
Yeah, and there was a whole art to it because you had to work at as low as 105, as high as 132. as low with the transformer minus 5% as high, and you've added up all your variables, and we didn't really have spreadsheets back then, so there was some art to making sure it'd work at low voltage and not burn up at high voltage.
Right.
So there was a needle, and sometimes you just couldn't do it. You just couldn't design a supply to do exactly what you need, and then you'd have to punt. This is real nice.
What's the range on this? It's half an amp.
It looks like it probably 20 volts. Probably 15 would have been the sweet spot I would use as a hobbyist. Plus or minus 15.
And the meter too, you can
right, just from each volts, of the
yeah.
right.
So
and right on the switch, it's got, again, this is a wafer stack switch. We don't really see that much these days, but it's got the resistors in soldered right to. So this is a great unit from Tom here, and he's got a cool story and his pictures of his Radio Shack there basically.
Yeah, he sent in a letter saying that. He said that my purpose for giving the supply away is that technology has changed and the requirements for power supply needs. That's true. The driver here is 5-volt logic. Is that 5-volt logic has nearly become a dinosaur, at least with the designs that I do at work. He says we now have 3.3 and 2.4. That's what we're just talking about. Logic with even lower voltage requirements for FPGA. I guess it's getting down close to 1.5 volts, or sometimes less than 1.5 volts.
My
1.2 volts.
One over there is 1.2.
2 volts. Yep. That's ridiculous, man. So he says I just did not have the heart to hack this supply. So yeah, good for you, Tom.
We'll give it a good home, I'm sure.
Yeah.
It's and show it off. I was going to stress test it and stuff, but it's almost, once I saw it, it's like, no, I know what it is. It's I can simulate in my head. I don't need to stress test it. Yeah. Well, why don't you get out what you've got?
Oh,
and
the other
if we have
item.
Time, then I'll
okay. We actually have two things. Thanks, Tom, for the awesome supply.
Very much.
And a great trip down Heathkit Lane. You know how we huge fans of Heathkit. Oh yeah. So all right. So we got this second item sent in by Scott Hennen, and it's interesting. He put the letter on this. Logarithmic
hey,
not quadrille paper, logarithmic graph paper.
Do it on Smith chart paper, then you're really showing off. And
he says, Fran and Bill, hello from another dinosaur. Watched the first 3 episodes, looks like fun. Well, thanks. Yeah, it's definitely fun on this end. I love seeing old stuff, and I have a bit of vintage gear myself. Still trying to find use for my old Heathkit H8 computer other than doorstop. Well, I think they'll probably have a few opinions on that. So he says, I have an interesting board here for you to explore. I bought 8 of these for the Nixie displays and sockets, so I guess he got them for the hardware. They're from an HP 5245 counter. And one day I'll make a Nixie clock out of them. Sounds pretty awesome. I was going to toss the boards out, but figured I could use the drivers on them. I looked up the transistors and came up with 40-volt NPN. Okay, so how do you control 200-volt Nixies with low-voltage transistors? The secret is hiding in the black box. Still, those take 60 volts or more. So that explains all the resistors. Have fun. So he wants us to explain how this could possibly work.
A safe way to control high voltage.
Yeah, well, this is actually an interesting board because these boards... did a little research, and HP came out with these in the mid-60s. It was before they had high voltage switching transistors or SCRs, and it was also after Nixies had been out a while. But when Nixies first came out and were first used in computers and for readouts and stuff, they were all electromechanically switched. And in fact, the early Nixie counter modules,
click.
Well, the early, you can Google it, but the early Nixie counter modules was basically like a motor, like a synchronized gear motor with 10 switches, and it would just go around and around and change the setting.
Even remember Star Trek, the chronograph was mechanical even.
Well, I've even seen on eBay and stuff these early Nixie clocks, and when you open them up, they're all electromechanical. They just basically got a gear motor and then just banks of switches that just ratchet and rotate. And so, but originally Nixies were intended to be switched mechanically, but as the 60s wore on, you wanted to switch them actively. And so how do you do that? How do you switch high voltage with a low voltage source? Well, this was a very sort of an inventive way of doing it with this black box.
Well, it's HP.
Yeah, it's
what's
HP.
their motto? Innovate or die or something
Yeah.
like that.
So what they're doing is they're switching the high voltage with photoresistors. There's actually a very intricate tree of photoresistors that use neon bulbs to turn on and off these various screens.
So I got a bunch of lights and a bunch of holes that I move around, or I turn
Yeah.
on different lights.
Well,
and
it's not even. It turns out to not.
my light's broken.
It's not even that simple because there's 8 bulbs
Right.
to display 10 digits, and they have this very sophisticated, weird.
So it's like a factorial
Yeah,
8 thing
this
right
is
off the bat.
This is the schematic. If you turn on that, look at that. So look at this Christmas tree. This is inside the black box. This tree of photoresistors, and they use a series of bulbs that are turned off in different combinations to turn on just the 10 different digits. But the interesting thing about this is how they get around the pre-biasing issue, because when Nixies were first used electromechanically, they didn't need pre-bias because only one element was ever active at any one time. When you mechanically switch a Nixie tube, there's no potential on the other cathodes. They can't draw any current. But as soon as they started using active elements and trying to switch with transistors or photoresistors, you have a potential where it can draw some current, especially through like
Sneak current, basically.
Right, yeah. So like if you use transistors to switch Nixies, there's always some reverse current. It draws just through the junction, and it started causing problems with ultraviolet. They'd start to glow purple. So if you're trying to actively switch a Nixie, you have to have some kind of offset voltage to stop the tube from producing ultraviolet emissions and just glowing with a purple glow.
Right. So it's kind of like you got to be able to. It's like having a couple ropes. You got to be able to jerk on the rope to a different voltage to do different things.
Right,
On is here, but pull it to here to stop it.
Right. If they're
like a cutoff valve.
Because the imperfect way that the Nixie's designed, it's a cold cathode tube. It's filled with neon, so it's conductive. The pre-biasing was done to take care of what they called objectionable glow. Whenever you read up on Nixies from the day, like 60s, 70s in the literature, they always talk about objectionable glow, which is ultraviolet, and they would tend to glow purple if they didn't have the right pre-biasing. So in order to prevent it from just drawing the current out of the other cathodes, you have to offset them with a positive voltage, which is called the pre-bias. And this photo resistor tree actually provides the pre-bias because they've paired up all of the elements with adjacent elements. So you can actually see like the 9 and the 5 and the 7 and the 1 are all paired. These are elements that are right next to each other in the Nixie tube. And so whenever one is on, it draws the pre-bias from an adjacent element through the photoresistor network.
And you were saying that this is probably a universal element that HP used in all kinds of their equipment.
Yeah,
it's standalone once you give it enough voltage.
Actually, there's very little known about these, but they were used in any kind of, I guess, computers, counters, meters, everything they made. So it is like a universal plug-in board. And I was going to try and power it up, but the specs show that it takes a 300-volt supply. And there's
and 3 other supplies or something, right?
300 volts. Yeah, it's plus 170 minus 130 just for the display driver, and then there's another plus 20 minus 15 for the transistors.
Yeah. In the old days of TV sets, you'd have 5 or 6 voltages, or an amplifier would have a bunch. But these days, we just don't have those kind of voltages laying around.
I do have the transformer to do it, but I just thought that putting 300 volts across a 60-year-old module would not be a good idea. But I did want to open it up. I figured we'd open it up and show the craziness inside.
Okay. Yeah, we're watching you take it apart.
I gotta cut these 2 wires here. You said that is a resistor?
Well, I measured the resistance. It looked like it was that. I'm not saying it's not an RC network or something like that.
Some kind of resistor.
The value on eBay just dropped by 3,000%.
Like I said, I wouldn't fire this up anyway. Oh, here we go. There's a gasket. Look at that. Light seal gasket right there. That's Hewlett Packard efficiency for you.
Try and hold it for you.
Right, there you go. So look at that. That's all silk screened on there, those elements. It's It's pretty impressive, actually.
Optocoupler logic.
Yeah, and
OCL.
well, look at the different sizing of the different elements. Obviously,
That's
the
cool.
Resistance, and look at some of them are
Wonder
doubled
if
up.
that's like a selenium or a cadmium deposit.
1, 2, 3, 4, 5, 6. Yeah, it's 8 bulbs. 8 bulbs, and what the hell?
That's our light source just came back on.
Great. Oh, actually, we needed that. There we go. So, well, that's cool. So, pretty insane.
Would you have said this is from the 60s or the 50s?
The 60s, yeah,
Okay.
mid-60s. I think this is actually date coded. It's got a date code in March '67. So.
Oh, so even a little later. But
Yeah, but I guess they came out mid-60s. I mean, the 74141 driver chip, I don't know when they came out, but it must have been like early 70s, 70, 71, 72 or something, that replaced the photo optical switching. And the 74141 is what people use today. The Russians made them by the bajillions, so you can still get them on eBay. And in fact, I think a lot of people sell the tubes with the old Russian chips. And the 74141 does the same thing. It has the paired off outputs where it pairs up adjacent elements in the Nixie and uses that sort of
Right.
reverse leak pre-bias to pre-bias the element that's next to the one that's on each time you switch one on. So it uses the same principle using diodes and transistors instead of resistors, but
so,
same idea.
tell me about mercury. You said there's mercury in this tube product.
Some, yeah. Because of the fact that with the Nixie tube being a cold cathode, there's nothing in the tube really to initialize the ionization of the tube. So when you actually put the high voltage to any one of the elements in the tube, you have to wait for some external energy source to actually
You trigger it off to ionize
yeah.
it. Yeah.
And so it's weird, but when you turn on if you have no external lighting source, or if it's in a totally dark room, you're actually waiting for like a cosmic ray or a high Z particle or something to hit the tube to start the ionization process and initiate ionization. And they found out, weirdly enough, that they started using Nixies like in coal mines and mining operations, and they weren't turning on. And it turned out it's because in pitch dark, where there's like no radiation, no light,
nothing to kick it
off, that they wouldn't turn on. So they started finding ways to make Nixies turn on faster and switch faster using mercury, putting a little bit of mercury in there to make make it more conductive.
Yeah. And so now we do it with LEDs to some degree, or?
You can get it. Well, it depends. You never know the Nixie you get. You see that some of the Nixies had mercury in them, which will turn on fast regardless of light source. Others, like the Jan tubes, they were actually doped with krypton 85, which is produces a beta particle. And they use that radioactive emission to be a constant source of energy.
Probably used in military equipment, because
The
they
Jan
never
stuff.
really cared about the military
Well, that's why I
operators.
said the Jan tubes were doped. So unless you know what you're getting, you could get the krypton 85 ones, or you could get the mercury ones, or you could get the regular ones. And then just to make it more complicated, they actually made a fourth type of Nixie for multiplexed tubes, because when they started multiplexing displays,
Right, you get ionization, sneak trails, and stuff
well,
like that.
it had to do with current, actually. The Nixies that were made for multiplexing had required much higher currents to turn on, just because of the way that they were building these multiplexed arrays. So if you get one of those, if you get a tube that's made for a multiplex display, it's going to require a lot more current to turn on than your standard Nixie tube.
And when you say turn on, you're saying that first we have to get the voltage up to the peak. And as soon as it starts to ionize, then we have to maintain the current so that the voltage doesn't just disappear on us again.
Right. The turn-on current is higher.
Stays there. Okay. So,
Yeah.
well, I found the major draw. I had it for less than a minute. I got this. We were talking about doing little Nixie tube modules, and of course I would use a 3-wire interface. I pull it out, drop it out of the box on the floor, which demonstrates what's bad about Nixie tubes. It's So I never even got to turn mine on.
Yeah, Bill emails me and says, "Oh, I
just got it.
I just got this in the mail," and then like 15 minutes later, he emails me, "I just broke it."
So, yeah, and there's interesting ways you can make the voltages these days.
Yeah.
You can oscillate almost anything and stick it through some caps and
Yeah, well,
give it a little treatment.
I wonder if you got the Krypton 85 version of.
Uh,
Well, I mean, okay, so for the viewers about...
you know, when I said we're not dead yet, well, you know, maybe we're dead and don't know it.
Okay, so before viewers even start putting the comments in and panicking, Krypton 85, it's got a half-life of 10 years. So you're talking about tubes that were made 50 years ago. It's
oh,
got
you don't mean kryptonite. You mean
no,
krypton.
Krypton 85,
okay.
yeah. It's an isotope of the noble gas, krypton. But the half-life is like 10 years. So after 50 years, it's pretty much got no oomph left.
I know the feeling. That's,
yeah. So I know that people be bummed out that we didn't turn this on, but
no, that's pretty cool though, with that opto gating or whatever you would call that.
Yeah, I just didn't trust the silk screening to be like viable enough to put 300 volts through it. But I don't know. I thought the chance of fire was greater than, but I did do a demo setup just to show a Nixie.
You want to show your breadboard?
Yeah, I'm gonna pull that out. Let me.
So here's your breadboard.
Yeah, I
true
built this
breadboard. That name, people don't
That's
think
right.
that it used to come from a breadboard.
That is exactly what it is.
Remember fan stock clips? Those little clips you push down, push the wire in. Push
yeah.
The wire
Well, if you grew up in the 60s, 70s, you first things you did was build things with light bulbs and wires, and they all had those little spring
it's
clips.
electromechanical. I mean,
Yeah.
It's because you couldn't do a tube.
No, it's like I think when I was in like an elementary school, we had science class, and like the first thing we did was just hook up a light bulb to a battery with those little spring clips. So anyway.
So show me your thing. You want me to plug it in?
Sure. Yeah. And here we go.
And the lights go out.
Yeah, let's put it on the close-up. Got it. All right, so there's Bill's just grounding the pin or putting pins high.
I'm just shorting stuff together.
Yeah. So this is Bill's right. This is a breadboard. I tend to do this again, going back to my roots. I start out with a piece of scrap wood and just bolt it to it. But I made a linear supply. There are some.
Well, you don't have to take it apart when you're done. First off.
Right. Yeah.
This is something. If you breadboarded like you're used to, then that's something you can pull out later and use a second time.
Yeah. Well, I built this just as a universal tester for Nixies. It's basically 200 volt DC supply, and then it's got it's also got room for an 80 volt pre-bias, which I didn't use for this model because it's using the 74141, which it provides 55 volts of pre-bias, so I didn't have to have a separate supply. And I've got a 5 volt regulated supply just for the.
Now, is that a US 74 chip, or was that a Russian?
This is a US
Okay.
because it's on the board. This is it's an American made. I don't know who made it, but like I said, there's
so, and we keep saying the Russians because they just stuck with the technology longer than we did.
Yeah,
right?
they were well.
It was still in production there in.
They were production in America too. I think I've got Nixie tubes that are Jan that were made in the 80s, and I've seen American Jan Nixie tubes that are decoded in the 90s. So they were still manufacturing them in America for military equipment.
Okay.
But the Russians did stick with tried and true stuff. I mean, they were still putting vacuum tubes in fighter jets. But yeah, this is just a linear supply. I used 2 transformers, which you.
So you went down a little bit, and you came
right.
back a slightly different amount, and got the voltage.
Exactly.
So they're
used
back to back.
2 transformers. I've got a 110 to 26.5 volt center tapped, which is the primary, and then the second one is a 220 to 24 that I flipped around and used the secondary as the input. If you do the math and of reducing that transformer to 25 and then 25 to 210, you
right.
think that you're getting like 300 volts or something like that. But when you do use the 2 transformers, you end up with significant impedance issues.
Funny math.
Well, it's impedance issues because you've got the difference in the resistance of the windings. You're actually putting the load into the high resistance of the secondary winding and getting the load, putting the load on
you would have to watch you don't saturate your inductor, and because there's 2 types of losses. There's the IR loss of the copper, as you just said,
right.
and then the inductive reactance of it, which but for something like this, you just stick them together and measure it, right?
Yeah, well, it comes out to about 206 volts.
Yeah. So you do have some other little things.
Well, this is just if you want to talk about it.
Well, it's just you brought some interesting things, some interesting examples
This is
of
from my other
construction techniques. Yeah.
My,
So you can see there's a little bit of 3D wiring going on here. So I just thought that was interesting. Because again, I'm more of a fan of if you build something, I like to be able to reach for it again. It doesn't cost a lot of money to keep your diodes already wired up versus the solderless breadboards.
that's the BCD. You can see I did that a little more condensed, but that's a BCD driver.
It looks like the schematic of a BCD driver if you look at it.
That is
just the way they're hooked.
That is a DTL decimal to BCD encoder converter.
So, yep, I do the same thing. I have a drawer over there of all my circuits because if I took the time to build it, I don't want to like repopulate a solderless breadboard.
Everyone is sort of enamored with the solderless breadboard nowadays, but they really weren't that popular when I was young, and they were expensive. I mean, I think I had one, but just one.
And they could be inconsistent. You'd sit there and wonder why it's not working, and you finally wiggle the one wire.
Well, the thing about solderless breadboards is the reason it's so popular today is because everyone's using them for digital stuff. Yeah. But if you grew up doing analog design, those solderless breadboards, they were the bane of analog electronics, because you would build something on there, and you get it working. You'd finish your schematic. You transpose that to a soldered board, and it wouldn't work, because the capacitance and the resistive issues.
People think about just the connection. They're not thinking about all the other metal under there that's not.
Well,
if you ever saw Robert Pease's little creations where he does the direct-to-direct wiring.
Point to point. Well,
that's how I learned to do it.
Yeah, point to point's the way to go, because the solderless breadboards, I mean, with digital stuff, it's not a big deal, but they're
not at our speeds.
There are significant capacitive issues with those. I think it's like 10 picos or 11 picos per rail of capacitance, and if you're doing anything of not even high frequency, but anything even not even anything in the low radio frequency, you can have significant problems.
You know what was a great example to help you visualize capacitance? Remember the variable capacitors 10 to 35 picofarad, where the fingers would interleave?
Yeah, the air gap capacitors.
Do you have any of those? Maybe bring one by next time, because I don't have one anymore.
Oh, like an air gapped capacitor.
But when you're learning about how a capacitor works, and you see that, you start to it's not touching, but it's pushing across, and the more that's close to the more that's there, the more it can push across, and you start to understand how a capacitor works.
Yes, anyway.
So if somebody else wants to send in something for us to look at?
Yeah, on the website, Bill's got the mail-in address if you want to send something for us to look at.
Dino-Den.com?
Yeah.
You'll put it up on the screen. It's there now.
It's on the screen. So, thanks. This is a blast. We'll do this again.
Yeah. Send your stuff in, and we'll tear it apart for you.
All right.
So, well, Bill Hurd.
Fran Blank.
Have a good day.
Bye.